linear equations. This kept coming in the past, right, when we solved Laplace's equation, Poisson equation, implicit equations, right. So, there were tridiagonal matrix which we encountered many times. So, today's class I will describe how to solve linear equations. So, we can write them in terms of matrix A, vector x which is unknown equal to B. So, this is how we will encounter these equations. Now, most of the time we encounter this to be n by n matrix, and this is n by 1 matrix, and this is n by 1 matrix, right. But there are occasions when it is n by m, okay, but that I will not discuss today at all. There are situations when you encounter non-square matrices. Okay. So, let us say we have this equation Ax equal to B. So, I am given B, I am given A, I have to solve for x. Now, you know already in your school days now, I think matrices are taught in schools. So, x equal to A inverse B, correct. But how do we find A inverse? So, A inverse involves determinants, right. So, the first, so I mean is 1 by determinant A inverse equal 1 by determinant. Now, the first entry is this matrix, submatrix, adjoint. So, it involves lot of matrices. So, for given n by n matrix, what is the complexity for computing determinant? So, I have to compute determinant, right, my minimum I need to do this, and these are also determinants, but of n minus 1 by n minus 1 matrices. So, how many operations do I require to compute a determinant? Okay. So, first how many terms are there? So, if you know the formula, so how do you compute determinant in terms of in computers? So, I will tell you the formula, okay. I mean this is, you have to do n loops. So, this matrix A, so first put the first index A0, A1, and the last one is An minus 1, the first, the row index, okay, this is row index. Now, the column index will come next, but they will be all distinct, right. So, for determinant, when I compute this one, this minus this, right. So, no two, so here all the rows are different and all the columns also must be different. So, the columns I call it J0, J1, Jn minus 1, and all the J's must be distinct. Now, how many J's do I have? How many combinations I will have? So, n factorial, because this can be any number, well, n minus, so this can be, yeah, this can be any number, it could be 0 as well, okay. J0 can be 0. So, this is n options, but once I choose this has only n minus 1 options, and so on, and the last one is you have no option, because last one will be fixed. So, number of terms I have like these are n factorial, and each of them involves how many multiplication? So, there are n multiplication, right, which is n minus 1 multiplication. So, for each of them I have to do n minus 1 multiplication. So, I multiplied by n minus 1, and then I have to do the sum. Now, sum, there is a sign, and the sign equal to what? If all the Ji is a cyclic combination, then it is plus. If it is anti-cyclic combination, then it is minus. Okay. So, 0, 1, 2, 0, minus. Okay. So, anyway, this is how you compute determinant. So, you can write a loop and you have to do product and do the sum. Now, this is very expensive. What is n factorial roughly? How do you compute n factorial? So it's some function of, well, I would like either exponential or power law or estimate. N squared, no. So what is Stirling formula? I mean these are very important, okay. Is n log n, right? Some factor plus, so is n log n. So this can be written as, so if you, so this is log of n to the power n. So n factorial is order n to the power n, okay. N factorial is huge, n power n, and your computer will basically crash if you give it to do 100 by 100 matrix. 100 to the power 100 is a big number, okay. So this is not a practical way to do it for large matrices. Large means even 100 is not going to work. So there were of course very clever people, and one of the cleverest person in mathematics, nobody will doubt this, right? So Gauss gave a scheme, and Gauss gives a scheme in which we can compute n inverse in order n cube. So not n power n but order n cube. So let me first do, instead of computing A inverse, we compute, let's try to solve this equation. So I will tell you the scheme, okay. So this is, I have made a simplified matrix, which I don't want to do a lot of algebra on the board. So this matrix has been simplified. So let's erase this stuff. So this is not what you do in computer. So in fact this will illustrate, among many other schemes which I discussed in the class, that what you learn in mathematics is not exactly what you use for computation. Okay, you have to come with a better scheme, and this is not what we will put in computer. Computer we do something different. So let's first look at the idea. In an upper diagonal matrix, convert this to upper diagonal matrix. So suppose I have equation x0 plus x1 is some number 5, 2x0 plus x1 is some number 3. It's always possible to eliminate this. How do I eliminate this? I can multiply this by 2. So equation multiplying any number doesn't change the equation. So multiply this equation by 2, then subtract this equation, the new equation, from this. So this will eliminate 2x0, 2x0. So the second equation after elimination will become, so this becomes 0, and x1 minus 2x1 becomes minus x1, and this one will be 3 times 2 is 10, so 3 minus 10 is minus 7. Okay. So the second equation is this. I use the first equation to simplify the second equation. So that's the same, this idea by Gauss is called Gauss elimination. You eliminate few terms. Elimination. So let's quickly work out what is done here. So in this equation I want to eliminate this term. So I want to make it diagonal form, upper diagonal form. So how do I eliminate this? So I multiply this equation by 3 and subtract. So what happens to the matrix? By the way, I have to do the same thing here as well, like I did here. So multiply by 3 except x0, x0 is unknown. So x0 should not be multiplied, okay, otherwise there will be a problem. X0 is not to be multiplied. So multiply all the numbers by 3, 3 becomes, so let's first, the first equation remains unchanged. This is same. This first one you don't do anything unless this entry is 0. Okay, so that I will discuss in a minute. Okay, first multiply this 3 and subtract. So this becomes 0. What about this term? 3 times 2 is 3 times 1 is 3. So 2 minus 1 3 is this one. This one is unchanged because 3 times 0 is 0, and what happens to this? 9 minus 10 minus 9 is 1. Okay, so and now I got up below equation as is it. Now I want to eliminate this this one because this is diagonal. Eliminate 1. How do I eliminate 1? Just add this equation. Okay, so when I add, what happens to this? Minus 1 is 4, and this one is 1 plus 10 is 1 plus 11 is 12. Okay, so this is my new equation. Fine. So what is the last equation? Last equation is very simple. 4x2 equal to 12, and you can solve that. Right? 4x equal to 12. What is the value of x2? So 4x2 is 12, implies x2 equal to 3. So here I eliminated this, called Gaussian elimination. Now I found the answer. With upper diagonal matrix, the last entry will be only one entry, and that is has only one unknown, straightforward. Next is, now once I know x2, then what is this equation? Minus x1 plus, sorry, yeah, minus x1 plus x2 equal to 1, right, this one. And so what should be value of x1? I substitute x2, which is 3, so minus x1 equal to 1 minus 3 will be minus 2, so implies x1 equal to 2. Once I know x1 and x2, then I can find x0 from the top equation, which is x0 plus x1 equal to 3. So just substitute x1, that gives x0 equal to 1. So my answer is, my x's are 1, 2, 3. That's my answer. Okay, so this is how it's solved. Now how long does it, what is the time complexity? Okay, so its time complexity is very easy to estimate. So imagine this n by n matrix. So all this, get rid of it. Fortunately this is 0 here. It helped us a bit. For me, I didn't have to do a lot of computation on the board. This, so I require n of them, correct? Same thing I have to do. So basically the first step, when I make this matrix below, n minus 1 by n minus 1, that is n squared. Now I have to replace this one by, so this line remains unchanged, but I have to make the bottom one by lesser, n minus 2 by n minus 2. That will require n minus 1 squared. Same operation, no? So multiply this, I mean basically you eliminate the first, I eliminate these guys. Then do the same thing again, eliminate these. So all the way up to 1. So this, what is the order for this? N square times n basically, no? So is order n cube. Now there are factors in front which is important. By the way, order n cube, say n cube, and somebody makes it 0.7 n cube. It's a big gain. Is it a big gain or not a big gain? 0.7 n cube is 30% gain, which is significant for supercomputers. Even 0.9 n cube is significant. But for estimation, I am not worrying about the factors, but there is a factor in front. But first we need to reduce from n to the power n to n cube. That's a very significant gain. But other gains are also significant, but not as much as this. Okay. So this how, so this part is called Gauss elimination. So I have converted this matrix A into upper diagonal matrix. This is called U matrix. Upper diagonal. This is a Now, so this is Gaussian elimination, but then after I have to keep finding x0 xi's. So first find the last one, then second last, third last. So this is called back substitution. Back substitution. Okay. So it involves two steps. First is Gaussian elimination, then back substitution. Okay. Now this is for solving Ax equal to b. There is only one catch. Sometimes I may get this entry to be 0. It's possible. Now then I can't eliminate this, right? Because I cannot multiply 0 multiplied by any number is 0. So what is done is you do some swapping. So this equation is same as this equation. I can make this equation go above and this equation come below. So we swap. So these are called pivots. Around the pivot you do action. This is a hero. For this operation. This is the main object. So we want this to be not 0. Hero can't be 0. So this has to become here, and we use pivot. So this is called pivoting. So we have to make sure that the diagonal is non-zero, but that can always be achieved unless there are like some anomalies could happen that none of the diagonals are zeros. Okay, but let's assume that that doesn't happen. So we can always swap. Okay. So with pivoting and Gaussian elimination you can solve these problems in n cube. In fact, this is how computers solve it, n cube. Okay, now this is way I can solve Ax equal to b. But somebody says, well, I don't want to solve this equation, but I want to solve for b prime. Now I have to do the same thing again, right? Ax equal to b, b prime, and order n cube again. So the better thing is to, if you use this equation again and again, or rather if you use this matrix A again and again for different b's, then compute inverse. And once you have the inverse, then how many operations will it take? It's not n cube. So I want to solve x equal to A inverse b. So this multiplication, matrix multiplied by a vector. So how many operations? So I have to multiply this number. So always, well, is a big writer, b0, b1 like this. So all these guys multiply here, so n operation, but there are n of these. So order n squared. Okay. So this operation is order n squared. Order n squared is cheaper than n cube. So I would compute A inverse for once and then use it again and again. Now how to compute A inverse? Now the idea which I will not discuss in the class, but we don't compute A inverse by computing determinant, but a matrix A where there is a theorem, it can always be written as product of L times U. Okay, L is a lower diagonal matrix, lower, and U is upper. In fact, L has a form, all the diagonals are 1s, huh? And L00, no, actually L01. I don't have in my computer. L01, then L02, L, what will that be? No, I am making a mistake. The L is of the, how would we write L? These are zeros. This is first row, the first index, then 0. Next will be L20, L21, L22 will be 1. Okay. So, but always diagonal is 1. And upper diagonal has, which I wrote, this upper diagonal. But these are all not equal to 1. This could be non equal to 1. Okay. But lower diagonal has always 1. So how many entries are there now in this L and U together? The number of unknowns must be same as n squared, right, otherwise there is a problem. If you have more unknowns you can't solve, if you have less unknowns also you can't solve. So, number of unknowns will be square, because this is diagonal plus upper, this is only lower, L is only lower, this is 1. Now, we can reduce A into L into U. Now, to be precise, sometimes this pivoting is a problem. So, there is a matrix P in front, P has entries, this for pivoting. So, computer adjusts in such a way that pivoting is proper, you do not have all this situation when there is 0 in the diagonal. So, these are of the form 0 0, there is only one here, it could be here, this could be here, like this. Okay. So, this is for pivoting, so P is for pivot, but ignore it, right now you ignore it. If the matrix is good, you can always reduce it to L into U. Okay. Now, it is again L and U are computed using elimination. Now, it is more algebra, but it is similar lines, and you can do that in order n cube. U computation can be done in order n cube. Once I have L and U, then I can compute A inverse. Is that correct? So, you do not need to, A inverse can be computed from L and U. So, let us compute, given L and U, how to compute Ax equal to B. So, let us assume that P is thus irritating, that is not there. Ax equal to B I want to compute, but somebody gave me A is L into U, Ax equal to B. So, I will call this as Y. Reduce this to L Y equal to B. Now, we can compute now this is a, as long as we have a diagonal upper diagonal or lower diagonal form, we can do easily. Again back substitution, right. So, bottom one can be easily computed. In fact, the last entry is the top one, you have to compute which one? Top one, x0 no y0 y1 b0 b1. So, where will I start? I shouldn't start from the bottom. Where should I start? Top. What is the top one? Y0 equal to B0. Okay. So, I compute Y0 straight away in one shot. Then I compute Y1. If I am going too far, I mean this is trivial, no? So, Y1 will be L10 Y0 plus Y1 equal to B1. Now, I already know Y0, so I can compute Y1. So, you go from the top. So, I can compute Y, how many operations? Order n squared, then order n squared. Because you see you always have n squared by 2 numbers. Okay, you can compute this. Now, once I know Y, then I can compute X now. So, what is that? Ux equal to Y, then X equal to by again this by, now this will be like exactly like this back substitution, what we did for Gaussian elimination. So, if I do that, then I can get X answer. Okay. So, that is how we will compute Ax equal to B using LU, order n squared. Okay. What about A inverse? Given L and U, can you compute A inverse? Sorry, that is right. So, B I have to choose properly. So, what kind of B I should choose? So, to get the first column of A inverse, I should choose just 1 0 0. So, that will give me X. X is, you can do as a homework, that is the first column of A inverse. Second one is put 0 1 0 0, compute X, that will be the second column of A inverse. So, you have to do again and again for each column, and that will give you A inverse. So, given LU, you can easily compute A inverse, and that is order n cube. I mean all of this will order n cube. Okay. So, once you have A inverse, then you can solve for any B. Okay. So, I did in quick succession Gaussian elimination and LU decomposition of any matrix A can be decomposed, and then how to find A inverse. Now, since we have done so far, we can quickly finish one more algorithm called tridiagonal matrix. Okay. So, we did encounter this tridiagonal matrices. In fact, this matrix is tridiagonal, I choose it that way. So, this is a tridiagonal matrix, diagonal, and one row above the diagonal and one row below the diagonal. Now, tridiagonal matrix you can do in or cheaper than full Gaussian elimination. In fact, I will follow the same scheme. In fact, I did what I did was Gaussian elimination for tridiagonal matrix. 3 diagonals, this one above, one below. So suppose I have n by n matrix, I have the diagonal, one above and one below, like this. So, idea will be to eliminate this. Once you eliminate this, then you get upper diagonal. And upper diagonal I know how to solve it easily. So, how do I eliminate? So, I do nothing but this. Okay. Next time I have 3 entries, 1, 2, 3. So, I have to get rid of this. How do I get rid of this? Gauss elimination. So, once you eliminate this, I am left with this one. Now, I have 3 entries here. What do I do? Eliminate, then I get 2 entries. So, each row will have only 2 entries, keep cutting it, and finally, the last one has how many entries? Last one has only 1 entry, because there are 2 entries, I get rid of this, I have 1 entry. So, we get a matrix which is after this operation, you get a matrix which is only diagonal and one diagonal. So, after the Gauss elimination, this one and this one. And how many operations will it take? Which order n squared? You can easily check it's order n squared. Actually, order n squared, order n is order n. It is really cheap, order n. Okay, because I have to do only one elimination each time, 3 times n. Okay, or is order n. So now I can easily solve. The last one is easy, no? Last one is this entry. Upper n minus 1 multiplied by x n minus 1 equal to b n minus 1. So, that gives you x, and then back substitution. Okay. So, tridiagonal matrix is solved very easily. In fact, you can write a very simple code, maybe 5 lines, and that will completely solve tridiagonal matrix. Okay. Python does it all. Okay. So, Python has functions which will we do not need to write the functions, it is done. So, I will show you how to okay. So, let us run these functions. Okay, let us first do linear solve. Okay. So, all these are part of linear algebra package of SciPy. Okay. So, from SciPy I have to import linear algebra. Okay. So, it is part of linear algebra. Now, I write a matrix A, it is the same as this matrix. I put a B, it is exactly what I solved, and so you have to use the solve function. It takes arguments A and B, it gives you x. If you want LU, then you say the function LU. So, the answer will come is P LU. P is that, I will show you what P looks like. It only has one in any row. and using u we can exactly like what I showed LU, we can solve for x in 2 steps. First solve for y, then solve for x, exactly what I did on the board. And I think you can, there is another way which is LU factor. Okay. So, this you can ignore, this can be done in one shot. Okay. So, let us look at how, how to execute this one. Is that clear? I mean the function syntax is trivial. Okay. So, run, I think it is lean solve. Okay. So, the first x is coming from this where I solved this one, first one solve, and second one is coming from this solution. So, let us look at what is A. A is this, what is L? L is this matrix. Okay. L is lower diagonal. So, their diagonal is 1 and this is 1/3 and this also happens to be 0. Okay. So, it is a simple matrix. Upper diagonal U. Now, this may not be, so this is a diagonal entry and upper diagonal, I mean these are the 3 upper diagonal entries. P is, the computer has intelligently tried to do not pivoting it dead for some benefits. So, P is not diagonal 1 1 1, it is 0 0 1 1 0 0 and 0 1 0. Okay. So, if I do LU, so dot product multiplication is not star. So, you do the dot product, multiplication dot product. So, dot, if I may just do dot A and x, that should give you B. So, that is AX matrix multiplication, that should give us B. So, that is B 3 10 11. Now, if I do dot of L and U, what should I get? I expect A, but I will not get A, it is staggered, A is switched. So, A is switched, see this one, so this is gone above, this swapped. So, the rows have been swapped. So, if I do dot of this with P, so PLU is A. So, I should dot this one with P. Okay. So, this is PLU and that will give A. Okay. That is same, exactly same as A here. Okay. So, this is how we solve for LU. Now, the next equation is tridiagonal matrix. So, let us look at tridiagonal. Okay, now entry of this argument is slightly tricky here. Okay. Now, the function we have to use is called solve banded. So, this is not only tridiagonal, but any banded, it could be 5 diagonals. So, I am using only 2 diagonal, 3 diagonal, one above, one below and diagonal. So, the idea is here, so if you have to look at this matrix, so this one is upper diagonal and sorry lower, upper first, upper. So, upper 0 is, you have to, well you have to give 3 numbers, but only 2 are non-zero, right, only 2 are non-zero here, only 2 are non-zero. So, the first one is set to 0, this is 0. So, 0 1 1. The second one is all diagonal 1 2 3. So, 1 2 3 fine, and third one is lower diagonal. So, 3 1 and there is a 0 outside. So, this 0 is not part of the matrix, but Python wants that it should be 3 by it should be order n, length n. So, this is a 3 by 3 matrix, but this is not the matrix, this is not the matrix A. Matrix A is this. So, argument I have to give is how many banded bands are there. So, one above and one below. So, this is one for one of them is upper and one of them is below lower, and this is AB matrix and B is unknown, sorry, B is the right hand side and that will give me X. Okay. So, had it been 5 by 5 matrix, well some bigger matrix with one more entry here, it will, you can get appropriately. Okay. So, this is how you give the, so this is simple one, but you could also make quite big matrix and you can do entries here. So, you can run this. So, AB is not the matrix, okay, that is the only thing I want to emphasize, AB is not the matrix. So, then So, this is my answer 1 2 3, okay, 1 2 3 is the answer x. Now, A is a real matrix, but AB is not the real matrix. Okay. So, this is the diagonal part, this is upper diagonal with one of them not there, and this is lower diagonal. So, this completes linear, well, part of linear algebra. I will do one more thing, then we will stop. This for solving Ax equal to b. Now, there is another important factor, functions are eigenvalues. Okay, you need eigenvalues all the time. So, Python does offer nice set of libraries. So, this for example, I mean this is trivial, but you can just use it. Given matrix A, you can compute eigenvalues and eigenvectors. So, if it is Hermitian, then it will be simpler, the computer will do less work. So, this H is for, so again is part of the linear algebra package, and this H is for Hermitian. Okay. So, you can put any matrix A. So, W will be the, I believe, the eigenvectors, and this is the eigenvalues. Okay, we will just check. So, if we run it, I find one of them. So, this will be 3 eigenvectors and there will be 3 eigenvalues. Okay. So, you know there are some tricky situations. So, every matrix A, which is n by n, how many eigenvalues can it have? N. Always proof, why those should be n eigenvalues? What? Okay, that does not, well, degenerate, yes, but why does it have n eigenvalues? Okay, the characteristic equation is nth order polynomial, or n minus 1, highest exponent is n minus 1. So, it has n zeros. What about eigenvectors? Is there a guarantee that they will have n eigenvectors? No. So, on which situation there is no n eigenvector, I mean there is no guarantee of n eigenvectors. What is the matrix? 1 1 1 0. Think of this matrix, this will have Jacobi form. So, you can, they are generalized eigenvectors. This one has only one eigenvector. So, you can work it out, x y. So, what are eigenvectors here, eigenvalues? 1, degenerate. So, this has 1 x y. So, there are 2 of them, but let me try to see whether I can get both of them. So, this x plus y equal to x and y equal to y. So, what does it tell you? So, y equal to 0 and x can be anything. So, the only eigenvector I get is alpha 0. So, there is only one eigenvector, it does not have 2 eigenvectors along x axis. Okay. Contrast this with, what about this matrix? One may say, what about this matrix, how many eigenvectors does it have? Now, this looks very similar, no, except this one I have made it 0. So, if I do it, x y is again 1 x y. So, x equal to x, y equal to y. So, I get identity, but you can choose any vector, in fact any vector, in fact any vector is eigenvector for this identity matrix, any vector is an eigenvector, but then you have to choose only 2 linearly independent. Okay. So, you can choose any 2 linearly independent eigenvector and this will work. Okay. Now, this matrix, so is that clear? So, but normally in physics we do not deal with this kind of matrices, in quantum mechanics, which is always Hermitian, this is not a Hermitian matrix, but in dynamical systems we encounter this matrix. In fact, oscillator has this one of the examples. okay, linear oscillator damped. Okay, this matrix, what is the determinant of this matrix? So the matrix is, now this is your math, this is not computation, 0. So it will have 3 eigenvectors, this one, this is a counter example, it has all eigenvalues and all eigenvectors. So what are the eigenvalues? So one of them must be 0. So product of eigenvalues is determinant. So one of them is definitely 0. The other ones are, so let's see, you can work it out. You prove this, this is a interesting eigenvector. So V and W. So V is eigenvector, okay, and W is the eigenvalues. So I get 2 zeros and one of them is 3. So corresponding to 3 is equal to, with, let me just, so 3 will correspond to 1 1 1, right. So eigenvector, so this x y z. So what does 3 correspond to? The eigenvector corresponding to 3, 1 1 1 will give you 3. So 3 will give eigenvector 1 1 1, it should have given actually. So computer can kind of help you to come up with your guesswork, and so this is NW V. So it is normalized, so it is 1 by root 3, it is 1 by root 3 with a minus sign, does not matter. So it is the diagonal. Now these are, so let us think of zeros. I need some more space. Is that equal to 0? Right, this is 0. So I get x plus y plus z equal to 0. So how can you satisfy this? X plus y plus z is 0, and in fact there are 2 of them. No, there are two eigenvectors. The 2 zeros, so there are 2 eigenvectors. So the idea is, in fact, from your complex analysis, so if I start with, let us see, I did not think about this, I am just thinking about this one. So 60 degrees, like this one and this one. So this complex vectors, these are vectors. So so this sum will give you 0. So I want to just think of e to the power I pi by 3 plus e to the power I 2 pi by 3 plus 3 pi by 3 minus 1 to the power I, okay, should give you 0. So this is minus 1. So these are, so I can make this x, y and z. Okay, these are Fourier transforms, right? So e to the power 2 pi by n, discrete Fourier transform. So these n, so these are the solutions. This is one solution. So x, y, z. What is the other solution? So e to the power I 2 pi, so I give the hint into 2. So remember what Fourier transform e to the power I 2 pi by n jk. So just multiply by 2, or I 4 pi by 3, 4 into 2 is 8 pi by 3, then for I 12 pi by 3, 3 pi. So this also gives 0. Okay. So there are 2 independent solutions, and this is how you can construct for any n by n matrix which are all ones. Okay. And these are real, but even these you can add and subtract. So you have to do some more work to get this. Okay. So this you please think about them and convince yourself that these are the solutions. Okay. So, due to lack of time I will just stop. So, linear algebra I completed. Matrix normally you need something like 3 lectures. It is a good idea to show how to compute LU. Eigenvalues are computed not again by the usual method. It is something called Q or decomposition. Okay. So, there is a numerical scheme. It is called Q or decomposition. And the reference is Newman is a good book. So, you can read if you like about values and eigenvectors.